So, hello everyone. Good morning to all of you. Today, let us begin with IEEE. Okay, standard for floating point numbers. What does this floating point number mean? Why we need to mention this in proper format? Let us say, for example, let us look at this. If you have a number 125.129. Okay, so this is one format of the number. Now, similar to this, what will happen? We have another number like 125.1290. Is there any difference between these two? Or same? Or same number 125.129000. Is there a difference between these three numbers? So technically we say that it is no difference, but how do the computer know that these three numbers are same or different? It does not know. So there's a requirement of a format which has to be understood here, right? So let us look at that. What is the standard of IEEE and what it says? Let us try to understand here carefully. Now, so this standard of IEEE is being brought up by uh, Institute of Electrical and Electronics Engineers. That's what the standard, we know it. Institute of, I stands for Institute of Electrical and Electronics Engineers. So it's like electrical, this stands for electrical, this E stands for electronics, and E stands for engineers. So this IEEE is what? So this IEEE is also referred by IEEE 754 standards. So this is an example of IEEE. Okay. So 754 standards we call it as. Okay. In that we have this floating point number standard. So in that again we have a single precision and double precision. Let us talk about a single precision now, and then we'll move forward to the double precision. Okay. So in case of this, let us talk about single precision. If we talk about a single precision here, this corresponding numbers will be of 32 bit. The first number is given by the sign of that, and the next is your exponent value, which is given by E dash, and the next is the mantissa part, M. Okay. So out of this, as I told, 32 bits it is. We start with 0, it will end up with 31. So this bit is 31 bit. So it starts from 30, it will go up to 23. So what is the meaning of this? It's an 8-bit number. So this E dash is an 8-bit number. So 8 is over and 1 bit is over, 9 bits are over. So remaining 23 bits out of 32 bits will be the mantissa part. So this is starting from 0 to 23 and 22 to 30. So in that way. Okay, sorry, 22 it will come here. Sorry, I apologize here. Yeah, and this is your 23. All right. So in this manner, we will get the numbers. Okay. Now let us see what is. There are three fields here: first field, second field, and third field. What does that first field mean? It's a sign field. The sign field is how many bits? The sign field is how many bits? It's 1 bit value. What about second field? Second field is called exponent field. What is that called? Exponent field. So exponent field is what? It is how many bits? It is 8 bits. So just a minute. It's an 8-bit value. All right. Now, and what about third one? Third one is mantissa part. So this how many bits it is? This mantissa part is how many bits? 23 bits. So this way we can able to understand the single precision format, and the single precision format is of 32 bits, which has been divided into sign bit, exponent bit, and mantissa bit. Okay, the sign of the number is given in the first bit. So this is the first bit, followed by the representation of the exponent, the base 2. This number will be represented in base 2, the binary number. Okay, of the scalar factor. Okay, so instead of the signed exponent e, we also can represent that as e dash. So this one, this e dash value, we can, how we calculate this e dash value? It's calculated by the exponent value plus the bias value. So what is this bias? We are seeing something new here, right? When I'm talking about single precision, not double precision. Okay. the value of this bias is 127 for single precision. So we can write E plus 127, E plus 127, we can write for E dash. So this is for single precision. Okay. So now this is also called as XS 127 format. Is also called as what? XS 127 format. The end value of E dash will be this E dash value what we got here, right? So this value can be 0 up to 255. How to come 55 we wrote? Because it's an 8-bit value. So what is 2 power 8? So that will give you 256. So we start with 0, it is 255. So that way we can able to write it. Okay. And one more thing, this is in case of 0 to 2. So we can represent this as 0 less than E dash less than 255. All right. So this way we can represent in case of a signed number. In case of that, if you want to represent that in case of negative numbers also, so it is 126 up to E up to 127. Someone should be equal, right? So this value will be equals to this also can be equals to. So this way we can represent the 32-bit number in what? Single precision. So what is that we wrote here? The example is for single precision. Same way we look at the double precision also for the IEEE standard. So let us look at the double precision. So what will happen if in case of double precision? So what? Okay, let us look at the same way. We'll change this. So in case of double precision, what will happen for this? Let us look. It's not single now. We are going to do it for double. Let us see the changes. What will happen for double? So we are trying to see double precision. So double precision single bit is same, 1 bit. So it will start with 63. Total 64 bits are there, 0 to 63, which means the length of this corresponding double precision will be 64 bit. Okay. Subsequently, I'll do the changes what we wrote in black color to blue color. That will be your double precision. So E dash value is 11 bit. It's not 8 bits here. Single precision 8 bit, right? So we're going to change it to 11 bit. So this will be 11 bit now. This also in binary. Now, what will happen to the Mantissa part? So can you count it and tell me total how many bits are there? 64 bits are there. So out of this 11 plus 1, 12 are getting over. So 64 minus 12, so remaining is what? 52 bit. So this 52 bit is for Mantissa. This is the format for the double precision. And what will happen? What will happen for this one here? For single bit, one bit value. So this one single bit is true. This is correct. Exponent value will vary to 8 bits, and it will vary to what? It is not 8 bits. It is 11 bit. And Mantissa is how many bits? 52 bits. So this way we can able to understand the double precision. And what about this E bias we told, right? E bias is 127. It is not 127. It become 1023. How much it will become? E plus 1023. So this is also called as XS 1023 format. And this value of this E dash will vary from uh, so 0 up to, let us look at this where it will vary up to. Okay, it will vary up to 0 to up to 2047. It will vary up to this number. Okay, so which means that here also we have to do the respective changes here for E dash. Let us rewrite that again for double precision and see what will happen for this. Okay, for this corresponding value, so this is going to be from 0 less than E dash less than 2047. And if you write that in terms of normalize that double precision value, we can also write that 64-bit representation, that actual exponent value will range from minus 1022 up to the exponent value, which is ranging up to 1023. So this is how we can able to understand the double precision part. Okay, is it clear? I just once again brief you out what is this IEEE standard. The standard for representing floating point numbers, it can be either 32-bit numbers or it can be 64-bit number. The standard for this is either 32-bit or 64-bit. It's been developed. This 32-bit format is called as single precision. Okay, The 64-bit format is called as what? Double precision. So this way we have the format of 64-bit and 32-bit. It's been developed by whom? IEEE. IEEE stands for what? IEEE stands for what? It stands for Institute of Electrical and Electronics Engineers, IEEE. It's also called as IEEE. What standard? 754, IEEE 754 standard. Okay. So for this 32 bits, we have to represent 1 bit per sign, exponent 8 bits, mantis at 23 bits. Whereas in case of double precision, sign bit is 1, exponent is 11, and mantis is 52. Okay. So this way we can able to do that and understand this IEEE standard. The next session, we are going to see an example of this. How do we represent that in a single precision and a double precision format? Okay. All right. Thank you.